Hi everyone. Let me take a look here. We've got the numbers are a bit low, 9 people in the stream, and our lag is pretty good today, or there's very little lag. So, can people let me know if you can hear me? Just let me know, and then we'll start. Can people hear me? I've got a green light over here, but it's always good to have confirmation. Okay, great. Thank you, guys. All right, let's begin. I assume people will stagger in as I go along. So, what should you be working on right now? The last video I gave you to watch was the one on vectors. It's pretty straightforward, and you can see on my whiteboard there I've got 6 questions on vectors, and that's not going to take us very long to do. Okay, so after that I've got 3 other questions that I'd like to do with you guys, and um, one of them is actually a question. The first one is a question that I didn't think of this when I did the live stream with you guys last time, but someone after in the live stream after yours said, "Can you give us some more practice problems to work on your own?" And I said, "Sure," and I gave them, but I didn't give them to you. But that's okay. We're going to go over them right now, and so that's questions 1 and 2. And then I've got a third question. I think we'll be able to get to it. That third question is actually an anticipation of 2D kinematics, which is what we're going to start next week. And next week, there's a little bit more video to watch. I think it turns out to be like an hour and 45 minutes worth of videos to watch. And I just thought we better look at the most difficult part about 2D. And so we'll start that. So you haven't really done this material for question number 3 formally, but I'll give you a little bit of a head start on that, and that should help you for next week. So that's what we're going to do during this lecture. Okay, so let's start off with these questions here. These are vector questions that are just converting. And to remind you what a vector is, we're going to move now from 1D kinematics, which is interesting, but I mean, it doesn't represent everything in the real world. We're going to move from that to 2D kinematics, and even 2D doesn't represent everything in all kinematics in the real world. It just represents kinematics along a plane. Real kinematics is 3D, but it's not that important to go to really 3D kinematics, especially if you're going to be in some kind of PT or exercise sports medicine type field. 2D kinematics is a plane, so it's something like we'll talk about uniform circular motion. That's like people running around a track, like in track and field. And so that's 2D because that has to be circles is a two-dimensional object. And so we got to ramp up our math for 2D kinematics. And to do that, we have to be able to describe the position, the velocity, and the acceleration in 2D. Okay, so those are the 3 main kinematic quantities: position, velocity, and acceleration. There's also time, but time is not a two-dimensional object. It's just a number, okay? And it's a number no matter how many dimensions you are. But when you're talking about like a position and you have, say, some reference point, like you remember like in one of the first lectures, I said, you need an origin, and I drew that tree, and I said, that's where our origin is going to be, at that tree, and that's where our 0 is. Well, even in 2D, you're going to have like an origin, and it could be like a tree, but now this tree is not on a line. This tree is like in the middle of a field. And I say, okay, walk, I don't know, 10 meters from that tree. And you look around and you go, okay, 10 meters from the tree, what direction? Or I say, there's like, I don't know, this box that you have to pick up off the ground. It's 10 meters from the tree. And you go, but what direction? Because 10 meters is 30 feet. Like you look around and you could travel in any one of like at any angle. And so in 2D, for a position, you not only need a distance, but you also need an angle. That's polar. The other way to do it is Cartesian, which is by x and y axis, and so that's why we have to do the mathematics of vectors. Okay, so just to summarize, position, velocity, and acceleration in 2D are vectors, and that means they're a pair of numbers. Okay, and time is still just a single number. That's called a scalar. Okay, so you'll see more of that next week when you take a look at when I introduce 2D kinematics formally. Right now, what I really want to do is start looking at just the converting, because it's going to be you're going to be converting so much that you want to make sure that you're able to do this without, you know, in a blink of an eye, without having to think about it too much. Okay, and so let me actually switch first very quickly to a whiteboard here like this. Okay, and actually let me zoom in a bit. Yeah, that's a little bit better. And so what you're seeing here is just this white plane. It's a plane. And so what we, let me get the right tool here, paintbrush. Okay, so let me draw an axis here like that. That's your plus x-axis. That's all you would need if this were 1D motion. But if it's 2D, then you're going to need, whoa, that's terrible. You're going to need another axis like that. And this is your y-axis, and you know you want to like, and somewhere in the plane here there's an object. I don't know, let's put it right here. There's my object, and here you are at the origin, and I want to tell you to go to that object, and so I need to tell you how far to walk and in what direction. Let me do that in red. You want to walk this way. Sorry, drew it. You want to walk this way like that. Whatever. Okay, and so you want to walk a distance r. Okay, and you want to walk at some angle theta, and we measure that angle theta from the x-axis. And so there's one way to specify the position. I could give you r and x. I could say walk 10 meters at, I don't know, 135 degrees from the x-axis, and you would find it. The other way to do it is to do the the Cartesian, and that is along the x-axis here. You look right underneath where that dot is like this, and you just project that dot down there like that, right onto the x-axis, and that dashed line is perpendicular to the x-axis, and that quantity is your x value. And you could do that again along the y-axis, just project it along the y-axis like that, and there is y. And again, you would find the object, because what you could do is you could walk along the x-axis, you would walk a distance x, you would turn 90 degrees and then walk a distance y like that. So walk along x and walk along y, and then you would get the object. Well, either I give you x and y, or I give you r and theta, you're going to find the object. So I could give it to you in two ways. So there should be a way of converting between the two, and that's what we're going to do right now. Okay, so let me switch back to the whiteboard. And so what you see here is it's fairly abstract. I just give you in questions A, B, and C, I give you r and theta, I give you the polar, okay, coordinates, and I say convert to the Cartesians. I actually ask for two things. I ask for the quadrant and for converting. And maybe I should go back to the whiteboard very quickly here. The quadrants, you should know them from math class, but just to remind you how these quadrants work. Okay, where is it here? There we go. Let me do the quadrants. I don't know. I've got a lot of colors here, so let me do them in green. This from 0 to 90 degrees, that's quadrant 1. From 90 degrees all the way to 180 degrees, that's quadrant 2 in here. From 180 to 270 degrees, that's quadrant 3. Okay. And from 270 degrees to 360 degrees is quadrant 4, like that. Okay. And that's going to be important to make this conversion work correctly. All right. So let me switch back to my whiteboard here. Let me look if there is any questions in the chat. Okay, looks like no questions. I know there's a bit of a lag, but I'll see if there's any questions in a minute, and if not, let's just convert. So the first one I say, look, I give you polar, and you know it's polar because it's r and theta, and I give you r is 7 meters, it doesn't matter what the units are, and theta is 35 degrees, and I tell you to convert, and you say, well, how do you convert? How do you convert from r and theta to x and y? So if I give you r and theta, the polar, I want x and y, okay? And the way to do that is pretty simple. And the formula is just x is equal to r cosine theta, like this, and I cut and paste that. There we go, like that. And the other formula is y is equal to r sine theta, like this. Okay, and it's just a matter of plugging in. All right, so I'll do it carefully this time for this one, but I think, you know, once you get the hang of it, it'll be pretty obvious. And then 35 degrees like that, and then over here 7 is your r, and then it's sine, and it's 35 degrees like that. Okay, and then just plug it into your calculator. I've already got my answers ready, so I'm just going to cut and paste them like this. That's going to equal this value right there, and that's going to equal that value right there. Okay, so I mean, one of the things you should make sure is you know how to do this on your calculator. Okay, and I mean, I can't show you because we're not physically together, but you know, like different calculators work slightly differently. So on like some of the old school calculators, you got to punch in 35 first, then press the cosine button, and then multiply by 7. You almost have to do it backwards. And some other calculators, most of the modern calculators, you could just go 7 times cosine, and it'll open up the bracket, and then you can type 35 and then close the bracket, and it equals, and it'll work. Okay, so make sure you can do that. And you'll get these numbers here. There's a bit too many significant figures there. I like to keep just 3 for the course. And so, you know, counting significant figures, you could see there I've highlighted the 5, 7, and the 3. Those are the first 3 significant figures on the left side there, or the figures on the left side. Ignore the decimal, it doesn't matter where it is, okay? And then we just take off the rest of them, okay? And same thing with that one, and then round up the 1. So for this one, 4.01, there's a 5 there, so round up the 1 to 2 like that, okay? So there's the answer to the first one. And oh, wow, what quadrant was it in? Okay, so what quadrant is this in? Well, you can see that a couple of different ways. It's 35 degrees, so it has to be in quadrant 1 because quadrant 1 is from 0 to 90 degrees. Okay, and the other way that you could see it is that for quadrant 1, both x and y are positive. Okay, and so the other thing you could say here is that this is in quad 1. All right, I guess we use Roman numerals for that. Okay, so let me know if there's any questions, because this should be fairly easy. And I'm just going to cut and paste for the next one, okay, like that. But this time, r is 3.5. So take out that 7 and replace it by 3.5. 3.5, like that. And the angle's not 35, but 225, like that. And 225, like that, okay? All right, everyone good with that? So again, make sure that you know how to do that on your calculator, and not to waste your time. You know, I did this before, and you just punch in the number, and you get this value here. Okay, and let me round that off like that. Okay, and you get negative 0.47 for your x value and negative 0.47 for your y value. Okay, they're identical, and I'll show you why in just a minute. Okay, and this is going to be in quad what? Well, again, 2 ways to see that. When your angle is bigger than 180 degrees but less than 275, you are in quadrant number 2. The other way you could see that you're in quadrant number 2 is that both x and y are negative. Okay, now why are these both the same value? All right, it's, I mean, when I did the it's somewhere, I don't remember which lecture it was, I showed you what like the cosine of 0 degrees is. I said the cosine of 0 degrees is 1, and the cosine of 90 degrees is 0, like that. Well, there's also the cosine of 45 degrees, which is a good number to remember. You don't have to remember it, but it's a good number to remember. It's 0.0707, like that. But guess what? Oh, I should probably show you the sine as well. The sine of 0 degrees is 0, and the sine of 90 degrees is 1. Okay, so let's just look at those two to start with. So cosine of 0 is 1, and cosine of 90 degrees is 0. So you could just do this on your calculator, and you'll see that it works. And sine of 0 degrees is 0, and sine of 90 degrees is 1. So you see that they flip. Okay. Cosine of 45 degrees and cosine and sine of 45 degrees, guess what? They're equal. Like that. They're equal. And that's because the cosine decreases as you go from 0 to 90, and the sine increases as you go from 0 to 90. And at 45 degrees, they actually cross. Okay? And so whenever you see an angle which is like 45 degrees or some multiple of 90 plus 45 degrees, you'll see that the sine and the cosine are the same. And you go, well, what's that got to do with 225 here, like that? Well, 225 degrees, you could write that as, guess what, 180 plus 45 degrees. Okay, and so whenever you've got, and of course 180 is 2 times 90. So basically, whenever you have a multiple of 90 degrees plus 45 degrees, then you could expect the sine and the cosine to be the same. It's not important that you know this. I mean, you've got calculators and you can see that, but it's good to see these patterns because what happens is first it gives you a deeper understanding, a deeper intuition into what sine and cosine are. But also, if you make a mistake, you'll recognize it. Okay, and so there you go. That's question B. Let me see if there's any questions in the chat. If x and y are both negative, shouldn't it be in the third quadrant? It is. And what did I write? I wrote quadrant 2. Haha. Thank you very much. I don't know if I said quadrant 2 or quadrant 3. It should be in quadrant 3. And Timothy, thank you very much for pointing that out. That was just an oversight on my part. Okay. And I was actually going to draw it. So I'm going to do that right now, actually. So when they're at 240 degrees, the first one was somewhere in quadrant 1. That's pretty easy to see. The 125 degrees is actually like there, like that. And so this vector is like that, and that's the 225, like that. And r is equal to, for that one, 3.5. Okay, and so you could see it there. You can see it there. It would be in quadrant 3. And also, if you were to draw those blue lines like this, like that, I guess I should have made that dash, but that's okay. You got the idea. Your y value here. Oh, your y value there and your x value there. Okay, the x and y value, they're identical for that one. Okay, so there's question number 2. Let's do our question B. Let's do question C. All right, and I think at this point you've got the hang of it. So let me just cut and paste the formulas there like that. Okay. All right, I'm taking out the values from the previous one because I cut and paste. All right, so what's R? 1.3. Okay, so it's like I'm telling you, walk 1.3 meters at an angle of 337 degrees. 337 degrees. Okay, like that. Oh, that's something else to be careful with on your calculators. Make sure you're working in degrees mode. So we both, in this class, we're going to use both radians and degrees. For this, for polar to Cartesian and vice versa, we're almost always going to use degrees. I can't think of a single example where we won't. Okay. Okay, so there it is. And then just plugging into your calculator, what did I get? I got this value for x, and I got that value for y, like that. Okay, and then rounding off. So this one I'm going to round off to 2 significant figures. The 9 has to go up to, well, the 19 has to go up to 20. So this is going to be 2, 0 there. And this one is going to be 1, like that. Okay, and now not to get egg on my face again, I'm going to be careful. What quadrant are we in? From the angle, you can tell that you're in quadrant 4. And from the x and y, you can tell that x is positive, y is negative. That's again quadrant 4. Okay, so the whole quadrant thing is a good way of checking when you're going one way from polar to Cartesian. When you're going from Cartesian to polar, the quadrant is essential because the formula actually changes a bit. Okay, so I think that's enough of the Cartesian, sorry, polar to Cartesian. Let's do now Cartesian to polar. Okay, let me see if there's any other questions in the chat there. All right, so there was a second question, and yeah, I answered that one. Okay, let me continue. Now, Cartesian to polar is a little bit more difficult. Okay, the R value is not hard, but it's the theta that's hard. And the reason for that is because the inverse tangent, which is the way I showed you guys how to do it. Incidentally, there are other ways to do it. You could do inverse sine and inverse cosine, but I'd rather just stick to inverse tangent right now when we do this because I don't want to confuse things. So I'll show you how I taught you how to do it with the inverse tangent in the pre-recorded lecture, and I'm going to do it that way here, and we're going to do it that way throughout the whole course so we don't introduce too many different ways of doing it. But just to say, like, if you've taken another course, with trigonometry and you had to do this conversion, you might say, well, we did it a different way there. I know it is possible to do it different ways, but I found that this way is the way that students tend to understand it the best. Okay, so if I give you the Cartesian values, x and y, what you want to calculate are r and theta. So you need a formula for r and theta. The formula for r is easy. It's actually Pythagorean theorem. And I showed you why in the pre-recorded lecture, but let me go back to the whiteboard again and just kind of remind you why Pythagorean theorem applies here. I don't know, I'm running out of colors here. Let me just use blue again. See this triangle that I'm etching out right there? Okay, so I just picked one triangle at random. Okay, that's a right angle triangle. Okay, and with a right angle triangle, you have the hypotenuse here, which is r, is equal to x, the square root of x squared plus y squared. My diagram is a mess right now, but r is basically the polar coordinate r is basically the hypotenuse, where the other two sides are x and y, and so they form a right angle triangle, and the hypotenuse of a right angle triangle is related to the other two sides by Pythagorean theorem, and the Pythagorean theorem says that r is equal to the square root of x squared plus y squared. Okay, so that's where that formula came from. I went a little bit fast, but again, you know, I did show you how that worked in the pre-recorded lecture. Okay, and so that's the same for all of them. So there's nothing really complicated with that formula. And I can't do the square root symbol, so I'm just going to write SQRT like that. And so here, just show you how the numbers get substituted in. For the x there, you're going to put in negative 3.4 like that. And for the y, you're going to put in 1.4 like that. Okay, and then you're going to square them. Now, be very careful here. See how there's a negative there? There's a negative there. That negative is part of the number that gets squared. And when you square a negative number, the negative goes away. So, you know, don't make the mistake. Notice where I put the bracket there. Notice I put the negative inside the bracket with the 3.4. Don't put the negative outside of that like this, and then accidentally just square the 3.4 and then negate it. You have to square the whole number, negative 3.4. When you do that, the negative goes away, because any number squared, the negative just drops out. Like negative 1 times negative 1 is just 1. Okay, and so that negative sign isn't going to make a difference. But if you put it in the wrong place, especially if you're punching it in your calculator, you can get an incorrect answer. Okay, and so that is going to equal, and let me just pull out that number so that I don't waste your time punching away at a calculator. It's going to equal this, and then rounding off, it will equal that. Okay, so I am going a little fast there, but I mean, I assume you know how to do that. Don't be afraid to stop me if you're like unsure how to do that. Okay, the only thing is if you ask me how do I do it on my calculator, that's going to be on your particular calculator. That's a little harder for me to show you, because it's going to be calculator dependent. But you know, during one of the Google Hangouts, I'll be more than happy. If you show me your calculator, I'd be more than happy to look at it and maybe try to figure it out that way. But there it is. Okay, so that's R. So not very deep at all. You know, just square the x value, square the y value, add them together, take the square root of that, and you've got the answer. Okay, Pythagorean theorem. It's theta that's the issue. Okay, and the reason it's the issue is because what you have to do here is you have to do the inverse tangent. And so this is usually how you write inverse tangent. It's like tangent to the exponent negative 1. You do the inverse tangent of the y value divided by the x value. And be careful, you have to keep the sign in there. So that x there, because it has a negative, when you put in the value for x, you got to put in the full negative 3.4. But that's not all. Sometimes you don't add anything. Sometimes you add 180, and sometimes you add 360. And you go, well, how do I decide? It depends on the quadrant. If you're in quadrant 1, don't add anything, or add 0 if you like. Add 0 degrees. If you're in quadrant 2 or quadrant 3, you have to add 180. Okay? You have to add 180 to that formula. And if you're in quadrant 4, technically you don't have to add anything, but I kind of like keeping our numbers positive. So you add 360. Okay. The reason adding 360 is the same as not adding anything is because how many degrees are in a circle? 360. And so if you get an angle like negative 60 degrees or you get an angle like 300 degrees, they're really the same angle. Negative 60 degrees and 300 degrees are the same angle because one is just measuring counterclockwise and the other one's measuring clockwise. Okay, if you don't quite get that or see that, don't worry about it. Let's always measure our angle. Let's always measure our angle counterclockwise from the plus x-axis. And I'm going to go back to my whiteboard and show you how that works in a minute. Okay, but let's decide right now what quadrant we're in. So x is negative and y is positive. That's quadrant 2. Okay, so we're in quadrant 2, and so we have to add 180 here like that. Okay, and over here you can just say quad 2. If you can't see y right now, when I go to the whiteboard, you'll see why it's actually quadrant 2. All right, let me see if there's any questions in the chat. Now everyone's good so far? All right, good. And we almost have no lag today, which is wonderful. All right, I can tell from I've got indicators here that show me if there's any lag. So I've got the y value divided by the x value like that. The y value goes right in there, and that's going to be 1.4. Okay, the x value goes in there, and it's got to carry that negative sign with it like that. And then of course we're going to add to that 180 degrees. Okay, and what did that turn out to be? So again, you might say, I don't know how to do that on my calculator. Well, again, I don't know. I can't help you right now, but I'd be more than happy to help you later. Okay, but do figure out how to do that. All right, and that turns out to be I've got here 158 degrees. Well, that number, but it rounds up to 158 degrees like that. Okay, so the answer, the full answer, is going to be, let me just rewrite it here. R is equal to 3.68 and theta is equal to 158 degrees. Okay, now we decided that this was in quadrant 2, so that was based on your x and y value. Is it in quadrant 2? Quadrant 2 is between 90 and 180. 158 is between 90 and 180 degrees. Okay, so there's the answer. Okay, and let me switch to the whiteboard, the other whiteboard here like that. And this diagram is now a mess, so I will just create a new one. Okay, and zoom in a bit. Let me see how that looks. Okay, good. Looking good. Okay, let me put an x and y axis on that. Here's my x-axis. All right. Here is my y-axis like that. Like that. And where was this? This was at negative 3.4. So you can imagine if I'll do this in blue, you move along the x-axis in the negative direction to negative 3.4, like this. Here we go, negative 3.4, like that. And my y value was 1.4, so that's positive 1.4. So that's, I don't know, it's like, I'm going to say it's like right about there. Okay, and I would draw a dash line up here. I'm not going to do that because I don't want to make too much of a mess, and I would draw a dash line here, like from the y, from that 1.4 on the y-axis, and where they meet, that blue dot, that's where the object is. Okay, and that's, the blue there is the Cartesian. If I switch to red, let me see if I can draw this carefully here. There we go. There's the r, and the value of r that I got. By the way, the value of r has to be bigger than the 3.4 and the 1.4. It's got to be bigger than both of them. Okay, and we got 3.68. Okay, I'm just going to write 3.7. All right, and that makes sense because it's bigger than the 3.4. Okay, and the angle, you have to measure the angle from the positive x-axis. So you start here on that positive x-axis, and imagine like you have the hand of a clock, but this clock turns counterclockwise. So it's going to start there, and it's going to turn. By the time it gets to there, it's only turned 90 degrees. Turn, and it gets to there, and you have reached, what was the number again? 158 degrees. So that's theta there of 158 degrees. Okay, 158 degrees. All right, so there you go. There's um, our Cartesian to polar conversion. Okay, I'll go a little faster for the other ones because if you have no questions with that one, it should be pretty clear. And so now what? Well, we're going to do this again. And let's do the R value first. There's the formula for the R value, like that. Again, R is going to be the square root of x squared plus y squared. X in this case is 1.7. Y is negative 2.2. Like that, okay? And again, for the purposes of squaring, once you square a negative number, the negative goes away. So whether you square negative 2.2 or 2.2, you're going to get the exact same number, okay? Saves you, like, I guess, one keystroke on your calculator and a possible error. So don't think that I just dropped that negative irrationally, like without thinking about it. I dropped it because when you square it, it's not going to make a difference, okay? And so if you just punch that through your calculator, I'm getting, rounding it off, I'm getting 2.78. There were some more digits, but that's it, okay? So again, I hope I'm not going too fast, but you know, if I showed you on my calculator here, it may not help you at all, okay? Because the calculator that I have on my computer is probably different than yours and so on, all right? So there you go, there's the first one, and then the second one is the inverse tangent of the y value divided by the x value, okay, so the inverse tangent of y over x, plus, and we have to decide what quadrant are we in. So if x is positive and y is negative, what quadrant are we in? Well, if you can't see it right now, it's quadrant 4. But if you can't see it right now, a quick switch to the whiteboard here and you'll see it. So if you're taking a look here, x was positive, right? So I'm doing Cartesian in blue. So x is somewhere along this axis here. It doesn't matter where, but it's somewhere along the x-axis, positive x-axis. And y was negative, it was negative 2.2. So y is somewhere along this axis down here, like the negative part of the y-axis, okay? And so if you're somewhere along there and somewhere along there, then you're in here. And that is quadrant 4, like that, okay? So you need to determine that for, to decide what to add here, okay? And so quadrant 4, you add 360, like that, it's 360 degrees. And you could just write to the side here in your notes, quad 4. Okay, quad 4. And now let me show you, what the number substituted in. Y is negative 2.2. Here you absolutely must put in the negative for y. Okay, so that y over x does include the sign. Otherwise, it doesn't work. Otherwise, the plus 360, everything gets broken that way, okay? So if you don't do that. And the x value is 1.7, like that. Oops, wrong way. There we go. Okay, so you take negative 2.2 divided by 1.7, get a number, and then take the inverse tangent of that entire number, and then plus 360, and that gives you, what does it give you? It gives you 308 degrees. 308 degrees, like that. Okay. And so the answer is R is equal to 2.78. Theta is equal to 308 degrees. Is 308 degrees in quadrant 4? Yep. Because quadrant 4 is from 270 to 360. Sorry, 275 to 360. And so it's in that range. Okay. Any questions? Nope, we're looking good. Last one. They're both negative this time, so we're in quadrant 3. So first the R value is x square root of x squared plus y squared. Negative 2.1 and negative 1.7, like that. Okay, so negative 2.1 squared plus negative 1.7 squared, then take the square root of all that, and you get 2.70. There's your R value. And then for theta, it's this equation here. But we decided we're in quadrant 3. How do we know we're in quadrant 3? Both x and y are negative. Okay? So if they're both negative, that's quadrant 3. And in quadrant 3, you add 180 degrees, like that. Okay? And so substituting in the numbers, negative 2.1, negative 1.7, like that. Okay, and that gives you a number. That gives you the value of 219 degrees, like that. Okay, is 219 in quadrant 3? Yeah, quadrant 3 is from 180 to 275. Okay, so there you go. Now, I left this one to the end because I really want to explain why this 180 there. Okay, so suppose for some reason I gave you this one, x is equal to 2.1 and y is equal to 1.7. Okay, so let's suppose that the question actually read, actually we can call that g, like this. Let's see what theta would be if you did theta. Never mind the r. The r value is going to be the same because the negatives there don't matter. But let's just look at the theta value. Okay, like that. Well, here you would have 2.1 divided, oh, no, I messed up, didn't I? Guys, I'm so sorry about that. That's negative 1.7. And this is 2.1. Okay, so it's the y value, which is 1.7. I'm glad I caught that. Negative 1.7 divided by the x value, which is 2.1. Did anyone in the chat catch it? You guys didn't catch it either. Okay, I don't feel as bad, but I'm the teacher. I'm not supposed to make mistakes like that. So the y values in the numerator, so 1.7 divided by the x value, which was 2.1, like that. Okay. Now you're going to get a value for that. I'm not even going to worry about that value. Okay, let's compare that with this one without the 180 in there. Okay, what are you going to get from the top one compared to the bottom one? You're going to get the exact same value, y. So this one is in quadrant 1. This one is in quadrant 3. And yet, they both give you the exact same value for theta, y. Well, take a look at this y divided by x value there, the y divided by x value. Notice that the y value is negative and the x value is negative. So if they're both negative, a negative number divided by a negative number, you could just cancel out the negatives. And so this value here, let me write it on the next line here like that, that value there is exactly equal to that value there. Okay? In other words, this value here, which should be in the third quadrant, actually turns out to be in an angle in the first quadrant. Now, why is that? Why does it turn out that way? Well, because the two negative signs here cancel. So just imagine if I take out that negative there, I'll put it back. When I take out that negative there, I'm going to put it back so I don't mess things up. That's going to just give you this other one, okay? And so suddenly, an angle which is in the third quadrant, because they're both negative, looks like an angle in the first quadrant because the negatives cancel. That's because this formula, inverse tangent of y over x, is kind of a dual. It's an inverse of the tangent function, and the inverse of the tangent function will actually have two solutions for any one particular angle. And so as a result, it can't tell the difference. Just the arctangent of y divided by x, I guess I should highlight that one. The inverse tangent of y divided by x can't tell the difference between first quadrant and third quadrant. And the reason, it can't tell the difference is because if both y and x are negative, so both y and x are negative, you're technically in the third quadrant, but it gives you an angle which is in the first quadrant because the negatives cancel out. And you say, how do you fix that? That's why you have to add the 180 in there. Okay, so that's just this part G that I just added at the end there. The reason I added that is to show you that, if you have this vector here, negative 2.1, negative 1.7, and 2.1, 1.7, they have the same R value because there's just as, the x and y's, once you square them and everything, do Pythagorean Theorem, you'll get the same value. But the difference is that one is in the third quadrant, one is in the first quadrant. Just the inverse tangent part of it will give you the same number. You have to manually go in and add in that extra 180 to make sure that it winds up in the third quadrant rather than in the first quadrant. Okay, and again, this is just a property of the way the inverse tangent function works. All right, I'll just wait a second, but that's it for converting vectors, okay? Because we had Labor Day on Monday, this week was a little bit shorter, and so I just gave you one video instead of two. But we have time, right? We have time. So what I'd like to do is I'd like to do some more problems with you, okay? And these are problems actually from last week. Two of them are from last week, and then there's one from next week, okay? And we'll see if we don't get them done. That's okay, because we go until about, I think it's 2:05 that we go until. But let's go ahead. So if anyone has any problems with what I just did, just type it in the chat right now, because otherwise I'm gonna go on to the next set of problems. All right. Well, there's a bit of a lag, but I'm not seeing anything, so let's go on. Let's go on. If you didn't get a chance to type your question, I'll come back to it. I will when I see it. Okay. So here are some little extra practice problems that I didn't think about giving them to you during last week's live stream, but I gave them to my other class. But I'm going to give them to you now, and we're going to go over them together now. Okay. And I do recommend that you look at them afterwards as well. Okay. So this is 1D kinematics, constant acceleration. I have here that I'm on the top of a building 40 meters high, and I throw a rock up with a velocity of 30 meters per second. How long before the rock hits the ground? And how fast is it going when it hits the ground? Okay, so 1D kinematic problem. The first thing in any of these problems is draw the picture, and the picture is drawn in 3 steps. Okay, so let me switch to my whiteboard, my other whiteboard, and let me create a new white sheet here, and let me reread that question again, because I've got so many variations. Okay, so I'm on the top of a building 40 meters high, and I throw a rock up with 30 meters per second. Okay, so the first thing to do is just draw, like, physically what you would see if you were there. Never mind x values or time or anything like that. That's going to be part 2. So here's a building, right? All right, there's a building, and I don't know, I can cross hash it like that. Okay, and here I am. I'm not even going to try to draw myself, but I'm at the top of a building here like that, and I've got this rock in my hand, and I throw it up, and on the way down it misses me. So it's not exactly 1D, otherwise it would hit me on the head, but you know, it just misses the side of the building and it goes down like that. Okay, so let me see what I said. I'm on the top of a building 40 meters high. I throw a rock up with a velocity of 30 meters per second. All right, everyone good so far? That's step number 1. Just draw the what you would physically see, as if you were actually doing this experiment. Okay. Now, step number 2 is to add both your x and time. Okay. So if this were 2D, you'd add x, y, and time, but this is 1D, so you just need an x-axis along the motion. Okay, parallel along the motion, and so that's like your ruler. And I'll do that in blue. Okay, and so here's a ruler, like this. Now, I'm not going to actually draw a ruler. I'm just going to draw an x-axis here like that. But think of it as a ruler. And I'm going to make my ruler positive upwards like that. Positive upwards. Okay? And since it's a ruler, you know, you get to place it any way you like. You get to choose where the 0 of the ruler is. I'm going to put the 0 of the ruler on the ground level. You don't have to, but that's a good choice. Okay? The other kind of obvious choice would have been here at the top of the building. But then when it hits the ground, it'd be at a negative x value. I kind of like keeping all my values positive, so there we go. Okay, now it's a ruler, right? So you could measure, and if you were to measure the top of the building here, let me just put a little dashed line. You would look at the side of the ruler here. What would you see at the side of the ruler there? Well, I told you it's 40 meters, right? Okay, like that. 40 meters high. So those are the only 2 markings that you have. You don't know how high it would go. Not without actually calculating something. I mean, you can calculate how high it would go, but you know, you wouldn't be able to read it off of the ruler directly. Okay, so there's the next step. Well, that's just the x. Okay, and actually, let me put positive x there, because you also need time, and time is just imagine you have a stopwatch, and you're going to hit the stopwatch at t equals 0, and say, well, where's t equals 0 going to be? How about when I throw it? That's my t equals 0 right up here. Okay, that's t equals 0. And then, of course, it goes up and comes down, and it gets to the bottom here, and you say, well, what's the time down there? We do not know. Okay, I don't tell you in the problem. Again, you can calculate it. You can, in fact, that's the first question. I said, well, calculate how long it's going to be in the air before it hits the ground. You can calculate it, but you don't know until you start doing calculations. Okay, this is step number 2. The stuff in blue is step number 2. Okay, so is everyone good so far? Step number 3 is we're not we're going to be plugging into these equations. You don't want to go directly to the equations, because if you do, you're probably not going to plug in the right values for x, x naught, or whatever. What you want to do is you want to read off of these guys, off of the diagram there, the values that you're going to be plugging into the equation, okay? And there's a set of them, and I guess I can do these in red. So I like going in this order. There's an initial position, there's a final position, there's an initial velocity, there's a final velocity. There's an acceleration, in this case an acceleration due to gravity, and there is a final time. That's the time down here. Okay, so there you go. 6 kinematic quantities that you can measure. All right, let's see if we can measure them. Your initial position. Where are you initially? That's where are you at t equals 0. Well, you're up here. That's what, well, I mean the rock. The rock is right there. I'll mark it in red. Okay, and so if you were to read that off of the ruler, off the x-axis, you're at 40 meters. There's your initial position. Okay. Then the final position. The final position just means, after some time t, at the point that you're interested in, well, it goes up. We're not at the final yet. We're not at the final yet. The final is when it is about to hit the ground. And so that is going to be, read it off the ruler there, 0. Okay? So there you go, 40 meters, t equals 0. The initial velocity, that's how fast I threw it. I said, let me reread it again, 30 meters up is what I said. So do this carefully. It's 30 meters per second, 30 meters per second, up, okay? And up is positive. So we're going to put a positive in there. Of course, you don't need to explicitly write in the positive, but I'm going to explicitly write that in there because positive means up. I could have changed this problem, and you might want to try this later as a variation. Imagine instead of me throwing it up and it goes up and comes down, imagine I throw it straight down at 30 meters per second. Well, then it's going to get to the ground faster. And then if if my problem, instead of saying I threw the rock up, I say I threw the rock down. Then you put a negative in there, okay? Instead of that positive, you have a negative. So be careful with that. Direction matters. Direction is critical. In the word problem, there's going to be some way that I indicate whether it's up or down. And, let's stick to the choice that up is positive and down is negative. And so up, positive there, okay? The final velocity, this one's always tricky because people will say when it gets to the ground, it stops, and therefore the final velocity is 0. That's wrong, okay? That is not the correct way to do it. Why? These equations, the 3 equations that I gave you, know nothing about the ground, okay? As far as those equations are concerned, and I can switch back to my black here, if the equation, all you had were the equations, the rock would just keep going down forever, okay? Because as far as the equations are concerned, this is just an infinite parabola extended both ways. Or another way to think about that is when the rock hits the ground, there's more acceleration than the acceleration due to gravity. There's also the acceleration due to the ground, and the formulas break down. So you say, well, what should I put in here for that final velocity? You don't know. And the way you should think about it is not the velocity when it hits the ground, the velocity just before it hits the ground. So that the rock is about to hit the ground, but it hasn't interacted with the ground yet. And because it hasn't interacted with the ground yet, it isn't accelerating due to the ground. It's still just accelerating due to gravity. And so, whenever you see how fast it hits the ground or when it hits the ground, in your mind, change the language to just before it hits the ground. Okay? And then you'll realize that you really don't know that value because you don't know how fast it's going down here. Okay? Before it hits the ground. And so, question mark, okay? If you put a 0 there and you use equation 2, which a lot of people will do, you'll get a totally wrong answer, okay? So make sure you understand this point here because this is a subtle point. Most people get it when they think about it for a while. They say, oh, well, the equations, they just don't take into consideration the ground. So I can't talk about it after it's hit the ground. I can only talk about it up to when it hits before it hits the ground. As close to hitting the ground, but not actually hitting the ground as possible, okay? Then there's the acceleration due to gravity, technically 9.8, but we're rounding off to 10 because it just makes life easier. Okay, like that. But which way does gravity pull? Gravity pulls down. So the acceleration is down, and down is negative. Up is positive, down is negative, so you better put a negative sign there like that. If you don't, the answer will turn out to be totally wrong. Okay, and then this time here, that's the time for the full flight until your final, which is just before it hits the ground. That is also unknown. And so you put a question mark there like that. Okay? The stuff in red is your third step in drawing the diagram. Okay? Trust me on this, even if you get good, do it this way, because when we get to 2D and then even other problems in this course, unless you're thinking systematically this way, you're going to start plugging into equations way too early and you're going to get the wrong number. Okay? I mean, I don't want to make that a strict rule, but you know, when things get too complicated, think it through in this particular order. Is everyone good so far? Because the next step is to plug into the equations. Okay. I don't know if I'll actually solve that for you. Well, maybe I'll get a. Oh, I know what I'll do. Yeah. I'll solve it part of the way, but not completely. Okay. And let's switch back to this like that. Okay. I mean, I don't want to totally do this for you. So how long before the rock hits the ground? Well, if you take a look at the three equations I gave you, there's only two of them that have time. So if you ask how long, so obviously if you're saying how long, you're asking to solve for time, right? And equation 1 looks like this. Okay, and equation 2 looks like this. And equation 3, I won't even write it down because it doesn't have time in it at all. So if you're asking how long, your equation had better have time in it, otherwise you can't solve for time, obviously. So it's either equations 1 and 2. But equation 2 you can't use because you don't know time and you don't know that final velocity. See why it was critical to make sure that you put a question mark there and not 0. Because if you put 0 there, you would solve for time, but it would be a totally meaningless time. So there's no way around it. You got to use equation 1. You're going to have to solve that quadratic problem. Okay. And now I'm just going to transcribe the numbers from the diagram. Your final position, you know what? I better write them down. Your initial position was 40. Your final position was 0. Your initial velocity was 30, positive 30, like that. Your final velocity was question mark. Your acceleration was negative 10, like that. And your time was unknown, like that. Okay. And so now we can substitute in the numbers. For x, we're going to put in 0. So I'm substituting in for x there, like that. Is equal to a half times the acceleration, which is negative 10, multiplied by t squared, like that. Okay, so a is negative 10. All right, plus v naught is 30, and then times t, plus x naught was 40. Okay, like that. Let me simplify that a bit. The half times negative 10 is negative 5t squared, plus 30t plus 40, like that. Okay. And I personally, oops, I need a 0 here. I personally like to divide through by the negative 5. It just makes using the quadratic equation so much easier. So negative 5 divided by negative 5, just t squared. Okay. 30 divided by negative 5, negative 6. Okay. And 40 divided by negative 5, negative 8. Like that. All right. And now, you know what? I'll solve this, but I'm going to show you, I'm going to give you a URL. And I copied and pasted it there. Unfortunately, you can't copy and paste that out of the diagram. If you're on a Google Hangout, I can copy it there. Or you know what? You could just Google for solve quadratic equation online. Okay. If you go to that website, it's just a quadratic equation solver. And so you don't have to even use that quadratic equation that you've learned in high school, you know, the minus b plus or minus b squared divided by minus b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, you don't even need that. You just plug into this and you get the answer. So let me do that right now over here. 1 and what was the other one? It's negative 6 and negative 8. and I get two answers here. I get that for one answer for the time, and I'll round that off in a second, and I get that other answer for the time, like that. Okay. And now I'm just going to round off, so I'm going to get rid of all those decimals. I'm going to get rid of all those decimals. There you go. Those are the two times. And do you want the positive time or the negative time? It's pretty obvious in this case you want the positive time because, you know, when you hit that stopwatch, that's t equals 0, the time only increases. Okay, and so that answers it. That answers the question. Okay, I hesitated whether to solve the quadratic for you, but you know what? Why don't you guys just find an online site that actually solves the quadratic and use that? Okay, and by the way, some programmable calculators will do it for you too. Okay, the negative one, you go, well, what does that mean? Well, remember what I said a minute ago, that the parabola extends infinitely far in both directions. Let me switch back to the whiteboard here like this. So where are you at t equals 0? Well, you're at that red dot right there, right here. This is where you are. If you were to, and the black path here, that is time going forward. Let me use I don't know, green here. Imagine you could run time backwards, and imagine, you know, the rock could just travel through the building. If you were to run the time backwards, if this is 0, then this is negative, like negative half a second, negative, 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 and you would be down here at negative 1 point, what did I say it was? Negative 1.12. Okay, like that. All right, and so you're there, t equals 0, you're here, and then traveling forward, you get to this point right here at t is equal to, what was the answer? 7.12. 7.12. All right. There we go. So that solves that problem. Let me see if there's any questions in the chat. No questions. I'm going to leave off. Let me switch back to here. Okay. There was a second part to this. The second part was, how fast is it going when it hits the ground? How about you guys try to solve that one on your own? Okay. For my other class, I didn't do this at all. Okay. I only did it for you guys because I didn't think about giving you extra practice problems, but I think I'm going to make that a bit of a habit from now on. How fast is it going when it hits the ground? Try to solve that on your own. If you're having difficulties figuring out what to use to get that, you can always catch me during a Google chat. Or, you know, for quick questions, email is good too. Okay, so you can certainly email me, and I usually answer pretty quickly. Okay, so try that one on your own. All right, and see, what time is it? We've got about another 20 minutes to go. Okay, let me look if there's any questions. So, chat is pretty quiet. If there are no questions, let's move on to the next one. The next one is actually pretty easy. It is an oscillator problem. Okay, and so the oscillator problems, the one I gave you in the assignment, is about as hard as it can possibly get. It's like I give you a Vmax and Amax, and I ask you to calculate omega, and you go, geez, there's no formula to do that. There's no formula that involves both Amax and Vmax. And I'll give you a hint, you have to combine two of them, okay? And they're pretty easy to combine. If you can't see it, of course, always ask me. But, you know, this one is fairly straightforward. So let's do it. An oscillator is found to have an amplitude of 1.4 meters. Okay, so amplitude, that's how far the oscillator displaces from equilibrium. And I said that it's 1.4 meters. The symbol given for amplitude is A, and that's 1.4 meters. Okay. By the way, you could, no textbook does this, but you could call that X max, like that. Okay. And the reason you might want to think about it as X max is because that's your maximum displacement from equilibrium. If equilibrium is 0, then X max is the amplitude, and in this case it's 1.4. Okay, now I call it A, and I'm going to call it A throughout the course because every textbook calls it that. But I kind of like thinking of it as X max because there's also V max and A max, and they are given the symbols like this. Okay, V max is equal to 25 meters per second. Okay, and I want you to give me the period. like that. And you go, well, I don't have a formula that involves A, V max, and T. Correct. But you do have a formula that involves omega. And let me cut and paste. Rather than type a W, let me see if I can get an omega from my word processor here and copy and paste that in there. Because let's see, is this going to work? It did. Great. Okay. So there's the symbol omega. It looks like a W, I agree, but it's actually got rounded bottoms, okay? And it's pronounced omega. It's the last letter of the Greek alphabet. So there's a relationship between omega and the period, and the relationship is omega is equal to 2 times pi. Oh, I can now actually even cut and paste the pi in there. Where's my pi? There we go. Copy, paste, 2 pi divided by t. Okay, so if I can get omega, then I can get t. Okay, well, you would have to rearrange it, but I'll do that in a minute. Okay, you obviously isolate t in terms of omega rather than omega inverse in terms of t. Now, I gave you A and I gave you V max. Is there a formula that has A, V max, and omega in it? And the answer is yes. It is V max is equal to omega times, times A like that. Okay, and you can use that now to solve for omega, because if I divide both sides by A, I will isolate omega, and I'll have that omega is equal to V max divided by A like that. Okay, so V max is equal to omega times A. Divide both sides by A. The A cancels from this side, isolating the omega, and on the other side you'll have V max divided by A. And that's going to be, well, just plug in the numbers, 25 divided by, 25 divided by A, which is 1.4. Let me work that out very quickly. 25 divided by 1.4. And I've got this number right here. And let me round it off like that. So I'm getting 17.9. And the units for omega are per second. Or you can also write it as, let me isolate that a little bit, okay? You can also write it as 17.9 hertz, like that. So hertz and per second are the exact same unit, okay? That doesn't still answer the question. That gives us omega. That tells us that omega is, let me write that on another line so that I've got it all in just one spot. So we now know that omega is equal to 17.9 hertz, like that. And you go, but I asked for the period. And you say, okay, how do you get that? Well, you use this one. But now what you do is you rearrange it, and multiply both sides by t, divide both sides by omega. So I'm doing two steps at once. I hope this isn't too much for you guys, but you would get this, okay? And you say, well, what did you do to go from this to this? Well, first I multiplied both sides by t. That eliminates the t from the denominator here, and then I divided both sides by omega, and that isolated the t on the one side like that. Okay, so a couple of steps, and now I can just plug in the numbers. 3.14 divided by 17.9, and that's going to give me 6.28 divided by 17.9, and round that off. Seconds, okay? So 0.351 seconds. So what that means is that it only takes 0.351 seconds for this oscillator to bounce back and forth once. Okay? So there it is. That answers that question. There was one other piece to it. What's the maximum acceleration? And let's look at the formula for a Vmax like this. There's the formula for Vmax. The formula for Amax, the maximum acceleration, is similar, but it's not omega, it's omega squared like that, okay? And so you actually have to square omega, and omega was 17.9, and A was, what was A again? 1.4, and it's just a matter of crunching this through your calculator. So 17.9 squared multiplied by 1.4, and so it's 449 meters per second squared. Okay, by the way, that's huge. That's a really big acceleration, okay? And you might say, how do I know that it's big? Well, what can you compare accelerations to? A typical acceleration, one that you experience every day, is acceleration due to gravity, 9.8 meters per second squared, okay? And this is, let's see, 100, this is 50 times bigger. So that's like 50 G's, okay? So that's a huge acceleration. All right. So fairly straightforward, these problems. I mean, I don't think I can make it much more complicated than this. I think the assignment is just a little bit more complicated because I give you Vmax and I give you Amax. But I think you can almost see how you would get it if you have both of them. Because if you have this equation here and you have that equation there, they differ by just an omega. And so if you divide one by the other, you get an isolated omega in terms of the ratio Amax divided by Vmax. And that's how you can get it, okay? I'll let you work that out. And again, if you have any problems, I mean, email me or catch me on Google Hangout in the evenings. All right. So we've got about 10 minutes left to the class. And I just wanted to show you how to start setting up these 2D kinematic problems, okay? And the reason I wanted to do it as part of this lecture, even though we haven't seen this material formally yet, is because we just did vectors, okay? And why did we even do vectors? Well, the whole reason we did vectors was just because we have to express the position, the velocity, and the acceleration in terms of two numbers now, x and y values, okay? And so let me show you how that happens, all right? So we're not going to totally do this problem. I just want to show you how it gets set up. And that, I think, will help when you watch the pre-recorded video. So now I have a cannon at the top of a hill 45 meters high, and I fire a shot with a velocity of 350 meters per second at 30 degrees above the horizon. Let me show you what that diagram looks like, okay? So let me switch to my other whiteboard. Let me create another sheet here like that. And let me zoom in a bit so it's a little easier to see. Okay. And what's the first step? Draw a picture. Just of the physical layout. All right. So there's my hill. That hill is 45 meters high. I won't quite draw it yet. I won't put in the 45 meters yet. I'm just going to draw the hill. I have a cannon at the top of that hill. So terrible at drawing. So there's the thing, and there's the wheels of the cannon. Okay, all right, that's about as best I can do. Okay, so there's my cannon at the top of the hill, and then there's this one little piece of language here. It's a velocity of 35 meters per second at 30 degrees above the horizon. Okay, so let me draw this business of a horizon in blue. Horizon, if you look out to the horizon, you're looking horizontally all the way out to infinity. If you were up here beside this cannon and you looked out to the horizon, this is the dashed line. That's the direction you'd be looking in, along that dashed line there like that. Okay? Now when you fire the shot, I'll draw this one in black. The shot is fired at 30 degrees above the horizon. Okay? And so it's going to be fired up like this. And of course, that trajectory is going to start to bend down like that. And there you go. And then eventually, it'll hit the ground somewhere. Okay, so we're not going to do the whole problem, but again, I want you to see, first of all, that when we start asking about the kinematics of this curved line here, that's not 1D, is it? It's not 1D because it's a line in a plane. It's actually in the plane of your of your computer screen. Okay, in the previous problem where I threw the rock straight up, and it comes straight down, okay, or maybe just slightly off so that it misses the edge of the building and then continues straight down. But in all the kinematics that we've done up till now, we had just everything moving along a straight line. Not here. Here you're going to have both an X direction and a Y direction, okay? And so we got to really start using vectors at this point. All right, so now you need to put a coordinate system in here, and the coordinate system is you get to choose where to put it, but I actually told you we're going to place the origin at ground level just below the cannon. So what that means is, and I'll do the coordinate system in red, the origin is down here at ground. So this is ground level down here, like that. There's my ground level, and the origin is going to be right here, directly below the cannon like this. And you can already see that this is going to be an x-axis and this is going to be a y-axis there like that. Okay, there's an x and y-axis. And as soon as you see an x and a y-axis, you're in two dimensions. All right, you're in two dimensions. That means your initial position, and the question I have written there has initial position, initial velocity, and so on. You know what? Let's just do the initial position because I think that's sufficient for to illustrate why you have to use vectors here. Okay, that's really the only reason I want to do this. Why do I have to use vectors here? If I say initial position, a minute ago when we did the problem, let me write it in here. I just wrote x naught like that. But the problem is that one number is not enough. Because where is the cannonball, the shot at initially? Let me do that in, I don't know, I'm going to pick another color because I can. Purple, it's right there. There's where the initial cannonball is, I guess inside the cannon, like that. And if I were to ask you, where is it? Well, you can't just give a number because it's, if I gave you a number like 5, say 5 meters, well then you might say, well, is it 5 meters along the x-axis here? Like, would it be somewhere over here? No. Is it 5 meters along the y-axis? Yeah, but you know, it could be 5 meters. Like this is like the height of the hill here is what 45. Okay, now is maybe the time to draw it in. So here, if I draw in like 45 here, like that, on the y-axis there, like that, 45. All right. Yeah, if I say, you know, it's at y equals 45, well, it could be that's y equals 45. That's y equals 45. That's y equals 45. That's y is equal. Every one of those purple dots that I drew are 45 meters above ground level. Okay, what you need to do to specify where the cannon is right there is you need to say, well, along in the x direction, it's right above the origin, and if it's right above the origin, then its x value is 0, and it's up 45 meters, and so it has an initial y value of 45, like that. Okay, this is a Cartesian vector. Why? Because there's both an x and a y value there. There's both an x and a y value. You can't say where is the cannonball initially unless you say what its x value is and what its y value is. Okay, so if I say, you know, if all I said was y is equal to 45, you know, you might say, well, is it over here at this x value? Well, no, it's actually at an x value of 0. Okay, so x value of 0, y value of 45, and that uniquely locates the point where the cannon is. So you could see that, you know, like when the shot hits the ground here, so I didn't extend it far enough, but at some point the shot is going to hit the ground here. And let me do that in purple as well. If I said, so this one, red here, like that. That's this point right there. What if I said, where is it? What's its final position? Okay, a minute ago, it was sufficient just to give an x value, but not now. You're going to need an x and a y value. Okay, the x value is, well, actually you don't know, because you don't know how far along the x-axis you're going to go until you get to that point. But what's the y value? Well, that's right on ground level, okay? And ground level is 0. And so once again, to specify its final position, you're going to need two numbers, your x and y value. And remember how I introduced all of this? I said, you know, 2D kinematics, you've got vectors, and vectors in 2D always need two numbers. To specify any point on that black trajectory, you're going to need two numbers. Well, there's the story with the position. It's going to be the same story with the velocity and the same story with the acceleration. And you know what? I think this is good enough because this is all I wanted to show you. I wanted to show you why we even did the whole vector thing. Like, why did I introduce all this extra math and the conversion and stuff like that? And the answer is because in order to do the 2D kinematics, your initial position is going to be two numbers, x naught and y naught. Your final position is going to be two numbers, x and y. Your initial velocity is going to be two numbers, v naught x and v naught y. And I know that sounds strange. You go, well, isn't it just traveling? I mean, you read the problem. It says it's traveling at 350 meters per second. Yeah, that's the magnitude, but it's got an x component and a y component. In other words, it's got a velocity that it's traveling along the x direction and velocity along the y direction. So they actually have to decompose it into two different values. Now, that's in the video, and it'll also be something that we'll practice next week during our live stream next week. Okay, and so the velocity will have both x and y. The position has x and y. The velocity has x and y. The acceleration has x and y too. But that one turns out to be easy because the acceleration is straight down, and so there's no x component to the acceleration. It's purely just an acceleration along the y component. And time is not a vector at all. Okay, time is just time. All right, 2 o'clock, and we're at the end of the lecture. And so I hope this was helpful. I don't see any more questions in the chat. If everyone's okay, just give me I'm okay. Otherwise, ask a question. I'll hang out for a little bit longer. And if there are no more questions, then we could just end the stream. Okay. So let me chat here. Everyone. Okay. Any questions? All right. One all good. Yeah, great. Go Bills. All right, Noah, go Bills. All right, guys, I'm gonna end the stream, and you know, email me if you have any problems with this. All right. Bye bye.